hope I'm audible. Hello. Hi. Uh,
Yes, sir.
yes, thank you. Thank you. So, welcome back again. So, this is the final session for the Thermodynamics course by Professor Anand. But just to reassure to all the students who would be attending this session or who will be watching the recording for this session, so this is actually an additional session conducted by me as per the request from the NPTEL portal as well as the students. Like if there are any requests from the students, so one of the students here asked me to, if possible, to take the auto cycle and diesel cycle. So for that purpose, I will be taking two topics today that are not in the course. That is auto cycle and a diesel cycle, just as a answer to the request from the students. So I will be taking these two topics, auto cycle and diesel cycle, and moreover after that we'll take two problems, one related to auto cycle and one related to diesel cycle, and then that would be all for today's session. So today's session, like, if just as a reminder, if everyone to reminder to every one of you, it's not related to the course. I won't say not related to thermodynamics. It is related to thermodynamics, but not related to the given course. So auto cycle and diesel cycle were not included in the course and will not be asked in the examination for sure. But as an extension to the air standard cycles, that was Brayton cycle in the previous lecture that we discussed, I'll also be taking auto cycle and diesel cycle, just as a answer to request from the students. Okay. So with that, I think we can start. And moreover, today's session will not be that long. It will be very short. We'll only conduct two topics: auto cycle and diesel cycle, two problems, and that would be it. Okay. So with that, I think we can start. So if you recall, in the previous lecture, we discussed about Brayton cycle. Okay, so if you recall, I told that in general or in reality, for all practical purposes, this Brayton cycle, that is the working cycle for jet engines or gas compression engines, is an open cycle. It means that it is an open cycle. It means that the air fuel mixture or the combustion product, air fuel mixture will be taken inside the engine, and then will, after the combustion process and all the work producing uh, processes, the combustion products will go out of the engine rather than being circulated in the engine as a cycle. Okay, but for the ease of understanding and analysis, and to apply the concepts of thermodynamic cycles, that is, the work produced is equal to the net work produced in a cycle is equal to net heat produced or net heat interaction in a cycle. So in order to maintain that analogy and for the ease of understanding of these thermodynamic concepts, we approximate this Brayton cycle, the actual Brayton cycle, into an air standard Brayton cycle. That is, we consider this air to be the working fluid and consider that this air as a working fluid will continue to circulate in the cycle without being exhausted out from the cycle. Okay, so we consider air to be the working fluid. That's why these kind of cycles, these kind of approximated cycles, are known as air standard cycles. Okay, so similar to that, as in the last week as discussed, this is based this Brayton cycle was the working cycle for jet engines that are used in aircrafts. Similar to that, we have auto cycle and diesel cycle. Okay, so these two cycles are the working cycles for vehicles. Okay, day-to-day vehicles that we see, cars, trucks, all these things. So the working cycle for those engines are the auto cycle and diesel cycle. Okay, and similar to that, similar to Brayton cycle, here also in reality it's an open cycle. I will discuss that briefly. So it's an open cycle. The air fuel mixture or the fuel will come inside the engine, get combusted, and the combustion products, after the work producing processes, the combustion products will be exhausted out of the engine. Okay, so in reality it's an open cycle, but again, to approximate and for the ease of understanding, we consider it as a closed cycle in the analysis. Okay, so with that, I think we can start our discussion. Okay, so we start with auto cycle. So this, why? Because it's in chronological order. As you will see, that Otto cycle was the, among the Otto cycle and the diesel cycle, it was the first one to be invented, or I must say conceptualized. So, okay, so it was conceptualized in 1876. Okay, so if I remember the scientist's name, it was done by Nicholas Otto. It was a German engineer. Okay, so it's also known as the petrol cycle or the petrol engine, and this cycle is the working cycle for petrol engine or the reciprocating IC engines or spark ignition IC engines, where IC means internal combustion. Okay, so internal combustion, as the name suggests, it means that the combustion or the heat producing or the energy producing processes will be conducted within the system. Okay, and system in this case would be the cylinder in which the combustion occurs. Okay, so we'll look into that thoroughly. Okay, so why this is called spark ignition or reciprocating IC engines, it will become much more clearer when we discuss the work, how the engine works. Okay, so let us look into it. I hope the diagram is visible. So when before starting the detailed explanation, I think it's just better so that we can get familiarized with some of the terminologies that are used in this engine. Okay, so this structure, this black lines that we see here, is the schematic representation of an actual engine. Okay, or the cylinder, or in general this entire composition is known as the engine. So this is schematic representation of a working engine. Okay, or petrol engine in this case. So there are two valves or two valves, that is the inlet valve and the exhaust valve. Okay, so valve in general is a device that allows, is a, I must say, allows one way flow of the fluid. So inlet valve will allow the fluid to come in, but when it fluid tries to push out of this inlet valve, it will get stopped because of this design. Okay, it's design, it won't be allowed to go out from this side. Rather, since the exhaust valve is designed in such a way that the exhaust products can go out of here, but the air cannot come inside of it because of this design. Okay, it will, when air tries to push through this valve, it will stop the air from entering inside. Okay, that's why it is known as valve in this case. And there is one inlet and one outlet for a particular engine. Okay, for a single engine there will be one inlet and one outlet. Then there is a ignition spark. Okay, that initializes the combustion. Okay, so it will give us electrical spark. It will generate a spark that would initiate the ignition of the air fuel mixture. Then there is a cylinder within which the piston moves, and this piston is moved with the help of a crankshaft mechanism. Okay, the details of that we can, like, I think is not that I would say necessary for thermodynamics perspective, but in general, if you want to know, crankshaft mechanism is just a mechanism used to convert this rotary motion to reciprocating motion. Rotary motion, like the crank would try to rotate in a circular motion, but because of this mechanism, the crankshaft mechanism, it will generate an output motion of the piston to be in a reciprocating one. That is, it will try to move in a to and from. It will generate a to and from motion. Okay, the rotary motion of the crank via the help of a crankshaft mechanism would result in a to and fro motion or linear motion of the piston. So this to and fro motion is also known as the reciprocating motion. Okay, and then there is the inner dead center. There is the IDC or the top dead center, depending upon the configuration. Like if the cylinder is horizontally kept, so the top dead center terminology will make much more sense. And if the cylinder is kept in a horizontal position or not in a vertical position, then the inner dead center makes a much more clear sense. Okay, similarly, there is a bottom dead center. There is BDC, the bottom dead center, or the outer dead center, similar to the terminology as IDC and TDC, depending on which becomes more relevant depending upon the configuration. Okay, like if it is vertically kept, then it becomes bottom dead center, and if it is horizontally or kept or not in a vertical position, then it is outer dead center. Okay, and the piston usually travels between these two centers, that is between the inner dead center and the outer dead center. Okay, so the pistons to and fro motion is limited between these 2 points, that is the inner dead center and the outer dead center. Okay, and the distance between which this piston moves, that is between the inner dead center and outer dead center, is known as the stroke of the piston. Okay, so I hope the the schematic diagram of the engine is clear. Should I repeat it, or is there any doubt in this diagram?
You can move forward.
Okay, thank you. Yeah, so with this schematic representation comes the thermodynamics part, that is the representing these processes in terms of thermodynamic properties. Okay, so for that we need to take the aid of PV diagram or TS diagrams. Okay, so let us start with the PV diagram. So this diagram is the representation for the actual cycle. Okay, not the air standard cycle, but the actual cycle. Okay, let me just go through it once. So initially the piston is at the bottom dead center. Okay, it's at the bottom dead center, sorry, is at the top dead center. Okay, it's at the top dead center. So the volume of is at its least. Okay, it's not actually zero, because there is some cutoff volume, or I just forgot what this volume is actually called. I'm sorry for that, but there is a residual volume left for the ignition or the spark device to be kept, or and the valves to operate. So there is a cutoff volume kept here. Okay, for those to operate, and that's why it is also represented as a cutoff volume here. Okay, so I actually forgot that specific name, so kindly forgive me for that. So thereby the volume is not starting with 0. Okay, but it is at its least possible value. So it is at the inner dead center or the top dead center. Okay, initially the piston is at the top dead center or the inner dead center. Now what happens is that first the inlet valve would open. Okay, the inlet valve will open, and the air fuel mixture. So in general, in the case of petrol engines or spark ignition engines, the working fluid is an air fuel mixture, which is obtained by the help of a carburetor. So it's a mixture of air and fuel. Okay, so air fuel mixture will be taken in through the inlet valve. The inlet valve will open, and the piston will move downwards or in towards the bottom dead center, the outer dead center, and the volume of the system, that is this system, will increase since the piston moves downwards. So the volume will increase. Okay, so now it goes to 0.1. Okay, the volume has increased. Then for the second process, it will undergo a compression process. Okay, which is done in an isentropic manner. Okay, so after sucking in the air fuel mixture, when the piston is here, then it will move upwards during the compression process. Okay, for the work consuming process. So it will move up in an isentropic manner. So it will give us an isentropic compression. So once the piston moves inwards, both the pressure and the temperature increases. Okay, within the system, the pressure and temperature increases. Then after the pressure and temperature is increased, in the case of Otto cycle or spark ignition cycles, the air fuel mixture does not undergo auto ignition. Okay, so because of compression, the temperature and pressure does go up, but this rise in temperature does not necessarily it does not essentially ignite the fuel by itself. Okay, so still there needs to be an external agency that ignites or initiates the combustion. Okay, so to do that, a spark is initiated through this device, which initiates the combustion. Because of this combustion, the fuel starts to ignite and generate energy. Okay, and this energy is in the form of heat. Okay, so in general, so heat is given inside the system because of the combustion of the air fuel mixture. Okay, it basically generates heat, so it is taken as a heat input to the system. Because of that, the temperature and the pressure within the system again goes up. Okay, and after that, but the piston is still at its top dead center. Okay, so the volume is not changing while this heat addition process or heat generation process is being undergone. The volume remains the same. That's why it's a constant volume heat addition. Okay, after that, because of this rapid rise in the pressure and temperature, the combustion products expand the uh, volume or pushes the piston downwards very violently. Okay, so because of this combustion, the piston will move down very violently. So it will go down. Okay, and it will expand. Basically, it will push the combustion products will push the piston downwards, and thus produce work. So this expansion process from 3 to 4 is the work producing process. Okay, which produces the work that we can use to move our vehicles. Okay, so and this is done in isentropic manner, and because of this rapid expansion, both the pressure and the temperature of the system decreases. Okay, after the expansion stroke or the work producing stroke, the piston is now at the bottom dead center. To now, because there are combustion products still left inside this cylinder, the exhaust valve now opens, which initiates the exhausting or exhaust process. Okay, I'm sorry, the exhaust process. So the combustion products will start to slowly move out from the exhaust valve. Okay, and when this occurs, both the pressure and temperature of the system goes down. Okay, and heat is released in a constant volume manner. But since the even after the exhaust valve is opened, the combustion products won't go out completely. In order to completely push out these combustion products, the piston once again moves upward, which causes this what to say this exhaust products or the combustion products to move out of the exhaust valve. Okay, so it goes back to the its initial position, that is to the inner dead center, and the cycle continues. Okay, so is this clear, the working of the cycle, the auto cycle? Clear?
Sir, 1 to 2, we don't do any work there.
No, 1 to 2 we do work, right? It's a work consuming the process, right? We have to push the piston to move upward, right? It's a work consuming process.
But how are we pushing the piston upwards?
See, one way to one way to think is that the inertia of the what to say the crank, once it once the work producing process has pushed the crank pushed the piston outwards, basically, like, this work produced from this process is very very high compared to this one. So it pushes the what to say the piston downwards, which produces work and rotates the crank. Okay, but this crank is actually a very heavy, like it's comparatively very heavy, which stores these energies in terms of inertia. Okay, and the inertia of this rotating crank itself produces the necessary work to push the piston upward again. Okay.
Yes, sir, I understood that. My question is, how is the initial, the first movement going on? I mean, when we start the cycle, we start from 1 to 2. So we don't push the cycle the first time. The 3 to 4 process will not go on, and how we are moving the piston upwards? That's my question.
uh, okay. How to say it? Yeah, the one way to think is that initially when we start the engine, the process should ideally start from here. Okay, when we start the engine or initiate the engine through start the engine through our in the vehicle, it will actually start from this process essentially, and then the cycle will continue. Sorry, from this process, and then the cycle will continue. One way to think is like that, and it makes a logical sense, right? So once the spark is what is initiated, it will start the engine, carry on this, initiate this process, and then the cycle will continue. Okay. Yeah. Okay. So yeah, I hope this explanation was clear. So as I mentioned, in an actual, and yeah, and if you just can, if you could tell me like how many times the piston has moved upward and downward from this diagram, can you say? It's quite clear, but can you tell how many times the piston is moved upward and downward?
Piston moves upward 2 times and downward once, sir.
No, no, downward also two times, right? Say initially the piston was here, right, in the top dead center. So it
Yes, sir.
first moves up downwards,
Okay.
first downwards, then moves up in the work consuming process,
Uh-huh.
one outward, then moves downward in the work producing device, work producing cycle. So it moves down, then again it, to push the exhaust products out of the cylinder, it moves up.
Yes, sir.
So
Four
there,
times.
yes, there is two times upward motion, two times downward motion. So that's why these kind of cycles or engines are also known as four-stroke engines, because there are four distinct strokes undertaken to complete a cycle. Okay, starting from the infusion or the inlet of the air fuel mixtures and the exhaust of the combustion products. Okay, that's why these kind of engines are also known as four-stroke engines. Okay, and both the uh, this Otto cycle and diesel cycles that we are going to study today are these four-stroke engines. Okay, and these are the engines that are generally used in vehicles, that is cars, trucks, and all these things. But there's also a variant of these two-stroke engines. Okay, that I'm not going to cover today, but just for your knowledge, I'm saying there are also variants of two-stroke engines which are usually used in motorcycles. Like initially they were used in motorcycles, but now also some motorcycles also come with four-stroke engines. Okay, but usually they are using two strokes engine in the motorcycles because first of all, the very size of these two stroke engines are comparatively smaller than this four stroke engine. That's why fitting them inside these lightweight vehicles such as motorcycles, it makes much more sense. It saves the fuel as well as it can what to say make the very applicability of these vehicles, lightweight vehicles, more reasonable. Like if the uh, motorcycle has a very what to say heavy four-stroke engine, there's no point of being motorcycle. You can easily buy a car if you are not comfortable with this. If you do not want these lightweight vehicles. Okay, so that's why these two-stroke engines are also there. And in those cases, if I recall, generally the two processes, that is the inlet and the combustion, and say the exhaust and the compression, both these processes take undergo simultaneously. Okay, so those processes are undertaken simultaneously. So that's why this, just give me this, these two processes, that was inlet and combustion, is done under one stroke, and then expansion and exhaust are done in another second stroke. Okay, so the details of that I think you will understand when if you want, and if you study the two stroke cycles. But for today we are just covering these four stroke engines for both auto and diesel cycle. Yeah, so as I was mentioning, this in reality, this let me go back, this is the actual cycle for this working cycle for the petrol engines. Okay, or reciprocating engines. Now you know why it is called reciprocating engines, because of the reciprocating motion of the piston. Okay, and moreover, these kind of engines are also known as spark ignition engines. Why? Because the ignition process is initiated by the help of a spark. Okay, that's why it is also known as spark ignition engines. Yeah, but for our thermodynamics perspective, this Otto cycle has to be approximated as a closed thermodynamic cycle. That's why the inlet or the infusion of the air fuel mixture, the process of the infusion of the air fuel mixture and the exhaust of these combustion products, those two processes are disregarded in the case of Otto cycle from the thermodynamics perspective. Okay, so that's why you see there that this stroke is removed when analyzing this Otto cycle. Okay, so this is the air standard variant or air standard version of the Otto cycle. Now you see the cycle is a closed cycle, and all the other processes, that was the compression, the heat addition process, the expansion, the work producing process, or the heat rejection process are there, but the infusion of the airflow mixture and the exhaust of the combustion products, that part is removed. Okay, so this cycle, I hope it's similar to the one that we have already discussed, so I don't think I have to repeat, but still let us go to the TS diagram. Okay, that will make much more sense. Similarly, for TS diagrams, we start with point 1, which has certain entropy and temperature, and the isentropic compression, that is 1 to 2, can be represented as a straight line here. Isentropic compression, it increases the temperature and the pressure also increases. Then we undergo a constant volume heat addition process. So during the heat addition, both the temperature and the entropy goes up, but it is undergoing through a constant volume process. Okay. Now from 3 to 4, in the isentropic expansion or the work producing process, because of the expansion, both the pressure and temperature goes down, but the entropy remains constant because it is an isentropic expansion. Now from 4 to 1, again there is a heat rejection process which is undergone via a constant volume process. Okay, and because of this constant volume heat rejection, both the temperature and pressure will go down, but the volume will remain constant. Okay, so from this cycle, let us now look into the processes and the values of various processes and the values of this change in internal energy, work done, and the heat addition. Okay, so process 1 to 2, that is the constant, sorry, this is isentropic compression. The change in internal energy is given by CV T2 minus T1. The work done would be, the heat addition would be equal to 0 because it's an isentropic compression. Okay, and since we know that from the first law of thermodynamics, if Q is equal to del U plus W, and if Q is 0, then delta would be equal to minus W, or the work done would be equal to negative of the change in internal energy. So that's why W, or work done, would be CV T1 minus T2, that is negative of the change in the internal energy. Okay, and here we consider air as an ideal gas. That's why for a for the change in internal energy, we take the internal energy change as CV times delta T. Okay. Now from 2 to 3, which is a constant volume heat addition, the heat addition would be given by CV T3 minus T2. Okay, because it's an ideal gas and it's a constant volume heat addition. Okay, and work done would be 0 because the piston is not undergoing any motion, or there is no volume change of the system, so the PdV work would be equal to 0, and that's why, since this is equal to 0, then Q would be equal to delta U, so delta U would be equal to same as the heat addition. Okay, now process 3 to 4, we have an isentropic expansion, so heat addition again would be equal to 0, so the change in internal energy would be CV T4 minus T3. Okay, just taking the magnitude here, sorry, just taking delta U, so final temperature minus initial temperature, this will be negative because it is undergoing expansion and temperature goes down. Okay, and the work done would again be equal to the negative of the change in internal energy, so it will be CV T3 minus T4. Okay, now process 4 to 1 is heat rejection process, and in isochoric or constant volume heat rejection process. So work done is 0 again because PD work is 0, and heat rejection would be CV T1 minus T4. T1 is the final temperature, T4 is the initial temperature, so CV T1 minus T4, and this should be equal to the change in the internal energy, which is equal to CV T1 minus T4. Now if you just see, you will get the summation of the change in the internal energy, delta U, for all this process will be equal to 0, and delta W will be equal to, sorry, the summation of work done will be equal to summation of the heat interaction. Okay, this because this is a thermodynamic cycle. Okay, so now we look how to find the efficiency of this Otto cycle. Okay, so if you recall, we again take the aid of the general formula of efficiency, that is, just give me 1 minute. Okay, just give me 1 minute. So we take the general formula, that is eta is equal to 1 minus q out by q in. Okay, q out is the magnitude of the heat ejected. So this I think you already know, so I don't think I have to what to say, dive deep into it again. Okay, so so by now you will see that the q out in this case would be this one, right? Cv T1 minus T4. Okay, just give me 1 second. Okay, so the q out will be heat rejection, so heat rejection would be Cv T1 minus T4, right? And heat addition would be Cv T3 minus T2. Okay, so see here I have written q4 or q rejected to be Cv T1 minus T4, but see this is like if you just take the formula of initial minus final. Okay, but if you just check the magnitude, because T4 is higher than T1, then and we are taking here the magnitude of the heat rejection, so we will take the negative sign. We will take the negative of this, it is Cv T4 minus T1. Okay, just to take the magnitude of the heat rejection. Okay, so we will have eta efficiency as 1 minus Cv T4 minus T1 divided by Cv T3 minus T2, that is the heat added. Okay, here again T3 is greater than T2, that's why it's fine. So Cv will get cancelled out, so we'll have eta as 1 minus T4 minus T1 divided by T3 minus T2. Okay, so is it clear till now?
Sir.
Okay, thank you. Yeah, so as if you recall, in the previous lecture when we discussed about Brayton cycle, we specified that the efficiency was measured as a parameter, measured in terms of a parameter known as the pressure ratio, Rp, right? So similar to that, in the case of Otto cycle specifically, we define the efficiency or the thermal efficiency of Otto cycles in terms of a parameter known as the volumetric compression ratio. So as Lokesh, if I am not wrong, Lokesh rightly pointed out, this is the ratio of the volume at the outer inner dead center divided by the volume at the outer dead center. Okay, the ratio of the volumes at the inner dead center and the outer dead center. So we define RV as the volumetric compression ratio as V1 divided by V2. Okay, so V1 volume at the, sorry, I'm sorry, I think I reversed it. V1 is the volume at the outer dead center divided by V2, the volume at the inner dead center. Okay, and if you see, V1 would be equal to V4 and V2 would be equal to V3, because both these heat interaction processes are constant volume processes. Okay, so we define this volumetric compression ratio like this. So now our task is to, one way or another, define eta or efficiency in terms of RV. Okay, so for that I think we need to do some manipulation with these temperatures. Okay, so for adiabatic processes, we know that T by V to the power 1 minus gamma is constant. Okay, so how we do that, I think you already know, but I think I can do this for this particular time. For other processes you can do yourself. Okay, so starting from this, we know that P V to the power gamma is equal to constant is the PV relation for an adiabatic process. Okay, we do the same thing here, but we know that since we are taking air as an ideal gas here in an air standard cycle, so we know that PV is equal to RT. Okay, because it's an ideal gas, then P would be equal to RT by V, correct? So if you substitute P here in this expression, you will get RT V to the power gamma minus 1, because there is V gamma divided by V to the power gamma divided by V, so it will become V to the power gamma minus 1 equal to C. Now since R, the specific gas constant, is a constant, so we can take TV to the power gamma minus 1 is equal to constant. C by R we take as another constant. Okay, so from that only we can write T, since TV to the power gamma minus 1 is constant, or you can write something like T divided by V to the power 1 minus gamma is equal to constant. Okay. Okay. So with that, with this, we can write T3 by T4 would be equal to V3 by V4 to the power 1 minus gamma, or V1 by V2 to the power 1 minus gamma. Why? Because if you see here, V3 is equal to, sorry, not here. V1 is equal to V4 and V2 is equal to V3. So from that we can write V3 by V4 is equal to V1 by V2. Okay, to the power 1 minus 1 to the power 1 minus gamma. Okay. No. I think there is certain mistake here. So because see, just clarify. Okay, just one thing. I think I made a mistake here, so I will just correct it. Okay, so sorry. T3 by V3 to the power 1 minus gamma would be equal to T4 by V4 to 1 minus gamma, or T3 by T4 would be equal to V3 by V4 to 1 minus gamma. Okay, so I think it was correct only. So so it should be V2 by V1, then it would make sense. Okay. Yeah, now it's fine. Okay, so since T3 by T4 is equal to V3 by V4, so see, V3 by V4 now would be equal to 1 by RV, correct? V3 by V4 would be equal to 1 by RV, right? So we can write T3 by T4 to be equal to RV to the power gamma minus 1, okay? Just taking the negative of the power. So similarly, we can write it would be equal to V2 by V1, okay? Again, sorry for a mistake. Yeah. V2 by V1, okay? So now if you in this from this expression, okay, let me just move up here a bit. So from this expression, if you just take T1 to be common out of the numerator and T2 to be common out of the denominator, you will get eta to be equal to 1 minus T1 times T4 by T1 minus 1 and divided by T2 by T3 by T2 minus 1. Okay, so so from now what we can see that just give me 1 second, then we will see that from this expression, okay, this one, this, so this will be equal to T2 by T1. Okay, so you will get T3 by T4 to be equal to T2 by T1, correct, from this expression. Okay, so from that you can write T3 by T2 to be equal to T4 by T1, right? Just take T2 here and T4 here, so we'll get T3 by T2 equal to T4 by T1. So now if T3 by T2 is equal to T4 by T1, then we can just cancel out these terms in the bracket, correct? So we will be left with eta as 1 minus T1 by T2, and if you just substitute this expression from this relation, you will get eta to be equal to 1 minus 1 by R V to the power gamma minus 1. Okay, so is it all right? So this is the efficiency for the thermal efficiency for the Otto cycle. Okay, okay, so I hope it is clear, because I won't then derive the entire derivation for the diesel cycle. I will like take the aid of this expression and just approximate it a bit. Okay, so I won't derive the entire expression for diesel cycle. So if it is clear, then I will proceed. Okay.
Yes, sir.
Okay. So now let us discuss diesel cycle. Okay. So most of the steps or the processes that we have followed for Otto cycle is quite similar to diesel cycle, but there are some certain slight differences that I will tell you now, that I will show you in this case. Okay. So but the entire process of intake of fuel, work consuming process, heat rejection process, work producing process, heat rejection process, and the exhaust, all these are quite similar. Okay. So I think now in this I will move a bit faster. Okay, I will point out the differences, but I will move down a bit faster compared to the Otto cycle case. Okay. So the structure of the engine, since it's a schematic diagram, so the overall structure of the engine is quite similar. All the terminologies are same. There is a crank, there is a connecting node, basically the crankshaft mechanism, and it is connected to the piston to generate the reciprocating motion. There is an inlet and an outlet, and an inlet valve and exhaust valve. Okay, but the key difference here is that the absence of a spark and the presence of a fuel injector. Okay, and the the working, or the I would say the inlet now infuses or intakes only air rather than an air fuel mixture. Okay, so in the case of Otto cycle, the inlet took air fuel mixture as the influx. Okay, but in the case of the diesel engine or compression engine, now you will also realize why it is called compression engine after we discuss it. There, the incoming fuel or incoming fluid is air only rather than the air fuel mixture. Okay, but rather than having a spark to ignite the compression or initiate the compression, to initiate the combustion, we have the fuel injector. Okay, so what this fuel injector does is that it sprays the fluid inside the cylinder in the forms of droplets. Okay, which increases the surface area of the fuel, that I would say that initializes the combustion in a much faster way. Okay, it initializes the combustion in a much faster manner. Okay, why? Because since the fuel is injected in the form of droplets, the surface area that interacts with the hot atmosphere or hot conditions inside the, or high temperature pressure conditions inside the chamber is much more the area that interacts with this high pressure and temperature region is quite high compared to this fuel being injected in the form of a jet. Okay, that's why this fuel injector is used, okay, rather than a liquid jet. Okay, so let us discuss the cycles again. Okay, so this is again the real cycle. So do you see there are quite similarities, but a key difference as well, that is, instead of having a constant volume heat addition, we have a constant pressure heat addition. Okay, so let us start from the beginning. So similar to the Otto cycle, the piston is initially at the top dead center. Okay, so the volume is at the cutoff volume. Okay, or residual volume, I just forgot the specific name of this volume. Okay, I'm sorry. So the engine is at the top dead center, the piston is at the top dead center. Now the inlet valve opens, that intakes air. Okay, so the piston moves down and reaches the bottom dead center, which initiates the intake of air. Okay, and the inlet valve is open. Okay, then it again undergoes a compression, which raises the temperature and the pressure of the air inside the cylinder, which again is an isentropic compression. Okay, during the compression, both the inlet and the exhaust valves are closed. Okay, so once the piston reaches the top dead the top dead center. Okay, it reaches top dead center, the exhaust valve slightly opens and the fuel is being injected inside the cylinder. Okay, the fluid is injected as a spray inside the cylinder, and since the pressure and the temperature inside the cylinder are so high, this atomized form of the fuel starts to auto ignite. Okay, because of the high pressure and temperature conditions within the cylinder, the fuel inside the chamber or the cylinder auto ignites. Okay, so there is no requirement of an additional or external source to ignite this or initiate this compression. Because of the high temperature and pressure itself, the fuel starts to ignite, and this ignition then again causes a rapid, just one second, causes a rapid expansion or rapid expansion of the piston. So piston moves down very rapidly. So you may ask, so but there's a slight increase in the pressure during this cycle as well. Okay, so I will let you know what this is. So as I mentioned, when the fuel is being injected, the exhaust valve slightly opens up and the piston starts to move slightly downwards. Okay, the piston starts to move slightly downwards, so that during this injection process the piston is moving slightly downwards. Okay, so that this fuel addition process occurs in a constant pressure manner. Okay, rather than a constant volume manner, it occurs in a constant pressure manner. Okay, because of the slight movement of the piston in the downward direction. Okay, and then after the ignition, this slight, I would say the slight increase in the volume of the in the cylinder is increased rapidly. Okay, so after the fluid ignites, the piston, which was slowly moving downwards, moves down rapidly and then produces the work. Okay, or the expansion stroke. Okay, similar to the Otto cycle. The only difference was that in the case of Otto cycle, the heat addition or spark addition process was in a constant volume manner. You could see something like this, but in the case of diesel cycle, it's done in a constant pressure manner. Okay. So once the expansion stroke is undertaken, the exhaust valve now completely opens, and because of this, there's a heat rejection and the combustion products slightly or slowly starts to move out of the exhaust valve. Okay, but again, similar to the Otto cycle, to push these combustion products completely out of the cylinder, this piston again moves upward, so that an exhaust valve is still open and moves the combustion products out of the cylinder completely. Okay, so again you can see, similar to the Otto cycle, there are 4 strokes. Piston was initially at the top dead center, it moves downward. First stroke, compression, it moves up. Again, work producing process, it moves downwards, and the exhaust process, it moves outwards. Okay, so you see, similar to the Otto cycle, there is again a 4 stroke cycle that completes the entire cycle of work production, and then basically which generates the motion in the vehicles. So you see, similar to the Otto cycle, is also a 4 stroke engine. Okay, but again, as I mentioned, there is again a 2 stroke variant as well, but we will not discuss it. Okay, so if you want, you can just read in the textbooks, but for vehicles, in most of the vehicles, it is a 4 stroke engine that is much more applicable. Okay, so is this cycle clear? The description of this schematic presentation and the PV diagram, is it clear?
Yes, sir.
Okay, thank you. So as I mentioned, in the case of this diesel cycle, it's a heterogeneous combustion and or droplet combustion. So it takes place in a constant pressure manner. Okay, so similar to the Otto cycle, again, since this is actual cycle, but for our from a thermodynamics perspective, we need to look in terms of a closed cycle, right? It's an open cycle, so as you can see, the air fuel mixture, sorry, the air comes in and the combustion products moves out, so it's a continuous inflow and outflow of the fuel. But rather than the actual cycle, for the air standard version, we need to remove this part. Okay, so that we can approximate it as an air standard cycle. Okay, so this is the air standard variant of this same cycle. Okay, so similar to that, we will again have, this cycle is already known, so I won't repeat it, but this is the corresponding TS diagram for this PV diagram. Okay, so you will see that process 1 to 2 again is an isentropic compression. So because of compression, the pressure and temperature goes up. Okay, the distinction is that the heat addition process or the heat generation process, because of the combustion of the fuel, is a constant pressure process rather than a constant volume one. Okay, so process 2 to 3 is a constant pressure process, so the temperature goes up but the pressure remains constant. Okay, and process 3 to 4 is and volume also goes up, if you recall. Okay, but process 3 to 4 is again isentropic expansion. Okay, so 3 to 4 is an isentropic expansion, and because of the expansion both the pressure and temperature goes down. Okay, then process 4 to 1 is a constant volume heat rejection, and because of the heat rejection again the temperature and pressure both goes down. Okay, so now if you see here, the slope of the constant pressure curve and the constant volume curve are different. Okay, in the case of Otto cycle it would have been similar. Okay, but in the case of diesel cycle the slope of the constant pressure line is lower compared to the slope of the constant volume line in the TS diagram. Okay, so this one we have discussed it again and again throughout the course. Now, as I mentioned, this becomes much more clearer when we are discussing the diesel cycle, since they are both constant volume and constant pressure lines. So that's why we can see that these two lines have to be drawn differently. Like conceptually, if anybody is going to check your answer sheet, when they see your diesel cycle diagram, they will see whether you have drawn the slope of this constant pressure and constant volume line differently or not. Okay, so this is important in that terms. Okay. So before starting the derivation or of the efficiency, again in this case I won't discuss the entire derivation. I will say do up to 70% of the derivation and give the final expression. The rest of 30% I will suggest that you can try it out yourself. There are standard textbooks, so I referred textbook by P.K. Nag, Engineering Thermodynamics by P.K. Nag. So there they have very thoroughly given the derivation. You can refer to that for your own interest. But for most of the cases, that is solving numerical problems or like that, you only need the final expression, okay, or the interpretation of the final expression. So let us start. Okay, so before that there are certain ratios that I want to discuss before starting the derivation, because instead of what to say, describing the efficiency solely in terms of a single parameter, the efficiency of diesel cycle is interpreted in terms of two separate parameters. Okay, first is actually the compression ratio, again RV, that is V1 by V2, and second is the cutoff ratio, okay, V3 by V2. Okay, this volume ratio from V3 to V2, since these volumes are different, the ratio of this volume V3 and V2 is known as the cutoff ratio. And why cutoff ratio? Because while the piston undergoes from 2 to 3, the fuel injection is cut off during that time. That's why it is also known as cutoff ratio. Okay, after 3 the fuel injection is cut off. That's why it's also known as cutoff ratio. And RE, that is the expansion ratio, that is the work done during the expansion stroke. So it is given by I'm sorry, I think it will be a bit confusing. It's looking like C, but it's actually E. Okay, RE. Now it is clear. The expansion ratio, that is given by V4 by V3. Okay, so these are the ratios that we will work with, but our final expansion will only include RV and RC. Okay, so let us see now how to do that. So similar to the Otto cycle, we will again create a table for different processes and see the values of change in internal energy, work done, and heat addition. Okay, so again this time I will just try to move a bit quicker compared to the previous one, because you already know all of this by now. Okay, so for process 1 to 2, which is, I think I should zoom out a bit. I hope this is fine, but both processes and the table is visible, so it will be much more clearer. Okay, so process 1 to 2, if you see, is a isentropic compression, so heat addition would be equal to 0, right? Change in the internal energy, since it's an ideal gas, is given by Cv T2 minus T1. Okay, and the work done would be equal to negative of the change in internal energy from this first law relation, so it would be equal to Cv T1 minus T2. Okay, process 2 to 3 is an interesting one, because now here all of the terms, there are some certain values and none of the terms are 0. Okay, why? Because in the case of Otto cycle it was a constant volume process, so the PdV work was equal to 0. But here, since it's a constant pressure heat addition, so there is a certain amount of PdV work which is seen here. So the heat addition is a constant pressure heat addition, so it is equal to Cp T3 minus T2. Okay, constant pressure heat addition. Then change in internal energy, since it is an ideal gas, For change in internal energy for an ideal gas is also always given by Cv T3 minus T2. So change in internal energy is Cv T3 minus T2. And the work done, since it is a constant pressure expansion, so work done would be P2, constant pressure P2 times change in the volume, this is V3 minus V2. Okay. Now from process 3 to 4 again, it is a isentropic expansion, so heat addition is equal to 0. The change in internal energy is Cv T4 minus T3, okay, final minus initial, and the work done would be negative of this from the first law. It will be Cv T3 minus T4. Finally, for process 4 to 1, it's again a constant volume heat rejection, so the work done would be equal to 0. Heat addition is Cv T1 minus T4 because it's a constant volume heat addition, and basically it's rejection, but if we consider final minus initial, you will see T1 is lower than T4, so it will anyway give you a negative sign. Okay. And that heat interaction would be equal to the change in internal energy, because from the first law, so the change in internal energy again is Cv T1 minus T4. Again, if you just sum up the total change in internal energy, you will get to be equal to 0, and summation of work and heat would be equal to each other. Okay, because this is a thermodynamic cycle, closed thermodynamic cycle. So I hope this discussion was clear. So if there is any doubt, you can ask. Otherwise, I will proceed. Okay. Okay. Now, for a this part is quite understandable. I think I can start with here itself. Okay. So efficiency, or eta in the case of real cycle, is again similar to the generic expression for efficiency. So it will be 1 minus Q out by Q in. Okay. The magnitude of Q out, we need to take the magnitude of the heat rejection. So Q out would be Cv T4 minus T1, and Q in would be Cp T3 minus T2. Okay. So in the case of Otto cycle, both were Cv, so these two will cancel out. But in this case, since it is a constant pressure heat addition, so it is Cp. Now we know that Cp by Cv is equal to gamma, that is the specific heat ratio. So we will have eta as 1 minus T4 minus T1 divided by gamma T3 minus T2. Okay. So I will again just so again I've defined the ratios again. Volumetric compression ratios RV is V1 minus V2, V1 divided by V2. Cutoff ratio RC is V3 by V2, and expansion ratio RE is V4 by V3. Okay. And again I mentioned why it is called cutoff, because injection of fuel is cut off once the piston reaches V3 from V2. Okay. So eta is again 1 minus T4 by T1 divided by gamma T3 minus T2, and there is a certain relation between RC, RE and RV, that is RV, that is the volumetric compression ratio, is equal to the cutoff ratio times the expansion ratio. Okay, so if you just do the multiplication, you will see that RC times RE will be equal to RV. Okay. Then similarly, we have for isentropic processes 3 to 4, we have T3 by T4 is equal to V3 by V4 to the power 1 minus gamma, or RE to the power 1 minus gamma. Okay, and since RE is RV by RC, so T3 by T4 would be equal to RV by RC gamma to the power gamma minus 1. No. 1 minus gamma. Okay, these are the mistakes that I do. Then T2 by T1, similar to the Otto cycle case, is equal to RV to the power gamma minus 1. Okay, so this you already know. I don't need to derive it, I guess. Okay, and if you just take now, and again T3 by T2 would be equal to V3 by V2, would be equal to RC, the cutoff ratio. Okay, so the main thing is that you know the ratios of these different temperatures in terms of these volumetric ratios. Okay, compression ratios, cutoff ratio, and the expansion ratio. So if you just substitute it back in this relation, taking some terms common out of it, you will see that the final expression that you get would be given by eta is equal to 1 minus 1 by RV to the power gamma minus 1 times 1 by gamma times RC to the power gamma minus 1 divided by RC minus 1. Okay, so at beginning it seems a bit complicated or very tricky to remember. Okay, so I also know it sounds difficult, but it will be just helpful like for your other exams, say GATE or any ESC or these exams, when they say, you try to remember this part only. Okay, because if you see the initial part, that is this part is exactly the same as the efficiency of the Otto cycle, right? Efficiency of Otto cycle is 1 minus 1 by RV to the power gamma minus 1, right? So it is just multiplied by an additional factor of 1 by gamma times RC to the power gamma minus 1 by RC minus 1. Okay, and see here the efficiency of the diesel cycle is defined in terms of both the compression ratio and the cutoff ratio. Okay, and this cutoff ratio is always greater than 1. Okay, it only makes sense, right? If I go back here, since V3 will always be equal to V2, right? Because in this process only the fuel is being injected, that's why this process has to be, V3 has to be greater than V2, and this will give you always a cutoff ratio to be greater than 1. Okay, and since RC is always greater than 1, you will find that this factor is always greater than 1. Okay, and if this factor is greater than 1, then the, what to say, if this is greater than 1, then this component multiplied by something greater than 1 will give you eta to be lower than the case when it was just substituted by it. So I will just give an example. I think it's quite understandable. Like, see, initially, say if you see, if 1 by RV to the power gamma minus 1, say, is equal to 0.4. Okay, so now if you do something like, and if this ratio, this factor is say equal to 2, right? So eta auto would be equal to 1 minus 0.4, right? But eta diesel would be equal to 1 minus 0.4 times 2, or sorry, so 1 minus 0.8 or 0.2, it will be 0.6. So the key takeaway from this argument or this discussion is that for the same compression ratio or the volumetric compression ratio, the efficiency of the Otto cycle is always greater than the efficiency of the diesel cycle. Okay, so this is a key takeaway from this argument. Okay, but there's again one more thing. Yes, is there any doubt? Okay, so there is again one more key thing to consider here is that okay, let me ask you one question. Okay, why do you think, like say in the case of Otto cycles, we saw that even after compression the air fuel mixture does not get ignited. Okay, and we need to use a spark to initiate the combustion. But in the case of diesel cycles, we see that the compression, after the compression, the temperature and pressure becomes so high that the fuel starts to auto ignite. Okay, why is that the case? Why doesn't the fuel gets auto ignited in the case of Otto cycle as well? Could you say? Just give it a try. There's a very key takeaway from this discussion. Okay, so for what I feel, and it seems logical as well, that in the case of Otto cycle and diesel cycle, the compression ratio, that is the volumetric compression ratio, is RV, for diesel cycle is always greater than the compression ratio for Otto cycle. Okay, so even if I'm saying that for the same compression ratio the efficiency of the Otto cycle is always greater than the efficiency of diesel cycle, but usually it's not the case. It's usually vice versa, because of the fact that the compression ratio for these diesel cycles are always like considerably greater than the compression ratio for Otto cycles. Okay, and in that case, since the compression ratio is so high, there is the fuel is being, the pressure and temperature of the fuel after the compression becomes so high that they start to auto ignite. Okay, in the case of diesel cycles, which is not visible in the case of Otto cycle, because the compression ratio is not that high enough to initiate the auto ignition. Okay, but It's just a one way to look into it, but again, when it some more experts in the field of combustion or these things argue that there might be some different scenarios, maybe because of the type of fuel also used. There are different factors that come into picture, but there's also one important thing to look into it. Okay, the compression ratio as well. Okay, so is it clear till now? Because this is all that we are going to discuss from a theoretical perspective. There are two problems, so I hope this is clear. Both of the cycles are clear. Hello. Can I proceed?
Yes, sir.
Okay. So there is one example. So what I would do is let me take the first example. Okay. The example for the auto cycle. I will take this example. Let us all focus together, and then there's another example for diesel cycle that I will give you some time to try, and then after that I think that would be all. Okay, so let us take this example. An engine working on the auto cycle is supplied by air at initial conditions are 0.1 megapascal and 35 degrees Celsius. Okay, so these are the inlet conditions for the air. The compression ratio is 8. Okay, RV is equal to 8. Heat supplied is 2100 kilojoule per kg. Heat supplied would be this heat addition. Okay, the heat generated after combustion. Calculate the maximum pressure and temperature of the cycle and the cycle efficiency. Okay, so one thing to note is that depending upon your notation, in this case according to my notation, point 3 is the point of highest pressure and temperature. Why? Because it is the point after the combustion or after the heat addition process. Okay, that's why it is the point of highest temperature and pressure. Okay, so you will see here also the temperature is highest from TS diagram, and from the PV diagram pressure is also the highest. Okay, so they are asking find the maximum pressure and temperature of the cycle, that would be the T3 and P3, and the cycle efficiency. Okay, and the parameters are given. Cp is 1.005 kilojoule per kg Kelvin, Cv is 0.718 kilojoule per kg Kelvin, and the specific heat ratio, specific gas constant for air is 0.287 kilojoule per kg Kelvin. Okay, so a good practice for both the case, for all these cases, is to draw both the TS diagram and the PV diagram, but most of the times PV diagram is enough. But since if you do not do the TS diagram, sometimes you may get confused which would be the point of highest temperature, but usually it is, or it's always the point after the heat addition process, at least for this auto cycle and diesel cycle. Okay, so we have T1, the initial temperature is 35 degrees Celsius or 308 Kelvin. So I won't say it's not only a good practice, but an important practice to convert all the temperature to the Kelvin scale when dealing with thermodynamics, basic thermodynamic questions. Okay, so it's just a general practice. Okay, so convert the temperature to the absolute temperature scale, it is Kelvin scale. Pressure is 0.1 megapascal. You can also write it as 100 kilopascal in fact, to just make your calculations much more simpler. Q1 or heat addition is 2100 kilojoule per kg, and volumetric compression ratio is 8. So since we already have RV, we can easily find the efficiency of the cycle. So eta cycle is 1 minus 1 by RV to the power gamma minus 1. 1 or 1 minus 1 divided by 8 to the power 0.4. Gamma is 1.4, so 1.4 minus 1 is 0.4. So we'll get eta cycle to be 0.565 or 56.5%. Okay. Now we have V1 by V2 to be equal to 8. Okay, because this is the volumetric compression ratio. So V1, since it is an ideal gas, since air is an ideal gas in this case, so V1 is R times T1 divided by P1. Okay, so V1 we will get as 0.287 times 308 divided by 100 or 0.884 meter cube per kg. So now if you know V1 from this expression, you can easily find V2, right? So it will be V1 divided by 8. So V2 is 0.884 divided by 8 or 0.11 meter cube per kg. Why do you need it? Because from V2, if you know V1 and V2, and since you already know T1, from this relation you will easily find the value of T2. Okay, so T2 by T1 would be equal to V1 by V2 to the power gamma minus 1. So I just took the, because you already used this one, right? T2 by T1 to be equal to V2 by V1 to the power 1 minus gamma, right? So just take the inverse, so it will become V1 by V2 to the power gamma minus 1. Okay, So T2 by T1 is V1 by V2 to the power gamma minus 1, or T2 is, so T2 by T1 is 8 to the power 0.4 or 2.3. So from that you can easily find T2, because you know T1. So we'll have T2 as 2.3 times 308, or 708.4 Kelvin. So now since you know T2, and more importantly you also know Q1, that is the heat addition. So Q1 would be, if you see here, Q1 would be, it's a constant volume heat addition, right? So Q1 would be CV T3 minus T2, correct? So you will have Q1 as CV T3 minus T2, and you know it is equal to 2100 kilojoule per kg. Since you know CV, since you know T2, you can easily find now Q1. So T3 minus T2, or 308.4, would be 2100 divided by 0.718, or to be equal to 2925 Kelvin, or T3 would be equal to 2925 plus 308.4, or T3 would be, would be equal to T max, that would be equal to 3633 Kelvin. Okay, so you got the maximum temperature of the cycle. So they have asked you to find the maximum pressure as well, right? So again you need to take the aid of this relation. It is P2 by P1 equal to V1 by V2 to the power gamma. Again this came from this relation, if you recall. PV to the power gamma is constant, so P1 V1 gamma is equal to P2 V2 gamma, or we will have P2 by P1 to be equal to V1 by V2 to the power gamma. Okay, this relation. Okay. So from that you know V1 by V2 is 8, is the volumetric compression ratio. So we have P2 by P1 to be equal to 8 to the power 1.4, or P2 by P1 is 18.37. Okay, now P2 is since it is 0.8, oh I tried the unit, right? P2 would be equal to 1. P1 was 0.1 megapascal, if you recall. So P2 would be 18.37 times 0.1, or 18.37 times 0.1, or 1.837 megapascal. Okay, so is it alright till now? Okay, so now you know that process, if I go back again, if I go back to this diagram, process 2 to 3 is a constant volume heat addition. Alright, process 2 to 3 is a constant volume heat addition. So for that, what we can do is, we know from the ideal gas law, let me just rewrite it. PV would be equal to RT, or PV by T would be equal to R, which is a constant, right? So for ideal gas, this ratio, this pressure times volume by temperature, would be a constant. Okay, so for process 2 to 3, we can write P3 V3 by T3 to be equal to P2 V2 by T2. Okay, or since it is a constant volume process, V2 would be equal to V3, so we'll have P3 by T3 to be equal to P2 by T2, because V3 is equal to V2, correct? So P3, this is a maximum pressure, or equal to P max, would be 1.837 times T3 was 3633 divided by T2. If I go back, T2 was 78.4, or you can write P3 as 9.426 megapascal. Okay, so is it clear, the analysis part? It's just a mixture of the ideal gas laws and all the concepts that we have discussed. So it's a good practice. All the concepts that we have discussed is revised while we solve this problem, because this is a very practical problem. So that's why I won't say exactly practical, but very application based question. So you see most of the concepts that we have discussed is now being rediscussed again. Okay, so I think you can try this question. Okay, try it out. I'll give you say 5, 6, 7 minutes. I'll wait. Okay, try it out. then we can discuss. Okay, so we have in an air standard diesel cycle the compression ratio is 16. See the difference. In the Otto cycle it was 8. In the case of diesel cycle is 16, twice the Otto cycle. Okay, so we have compression ratio is 16, and at the beginning of the isentropic compression the temperature is 15 degrees Celsius. Okay, and the pressure is 0.1 megapascal. These are inlet conditions because it's the before the compression is the inlet conditions. Heat is added until the temperature at the end of the constant pressure process is 1480 degrees Celsius. Okay, calculate A, the cutoff ratio, that is V3 by V2, or it's my terminology, so it's basically the ratio of the volume after the constant pressure expansion to the initial volume before the constant pressure expansion, and B, the heat supplied per kg of air, and C, the cycle efficiency. Okay, and D is MEP, or the mean effective pressure. So this part you can neglect. I will show you how to do this. So you can neglect D for now. Try A, B, and C. Okay, so I think I can show to this part. This is completely fine. Convert temperature, given temperatures to absolute temperature scale, and then try to sort it out. Okay, so I'll give you say 6 minutes. I'll wait till 5 minutes. You can try it out, then we can try to solve. Okay, a good practice is to draw the PV diagram and TS diagram, note down all the terms that you already know, and then try to see what are the relations that you can apply to sort out the unknown terms. For example, let me give you a hint. For example, this diagram, I think you can use this as well. Okay, so for example, for process 1 to 2, it's an isentropic process, right? So there are very well known relations. PV to the gamma, PV to the power gamma is a constant, or T by V to the power 1 minus gamma is a constant. So these relations you already know. Okay, given the known terms, you can try it to substitute those values and try to see whether you are getting the values of temperature and pressure at point 2 or not. Okay, try it out, then we can. And if there's any doubt, you can ask me. Okay, no problem. You can ask me if there's any doubt. Since you know the compression ratio, I think using the temperature relations, you can easily find the value of T2. find T2. Okay. So I think we can try the solution. Okay. Okay. Should I discuss the solution? If it is okay. So let us try. Okay. So as I mentioned, if it is visible, so since process 1 to 2, so there are many hints that you can take. Okay. First of all is this, all these processes are special processes. Okay, so all of these points are related to the other via some relations that are applicable for ideal gases. Okay, for example, process 1 to 2 is an isentropic process, so there are temperature volume relation, pressure temperature relations, and pressure volume relations. Okay, so from starting from PV3 power gamma is equal to constant, you can easily derive the other relations. Okay, the pressure temperature and the temperature volume relations you can easily derive. Okay, so you can take the aid of those relations to find the relation between the temperatures and pressures. Okay, first for process 2 to 3 is a constant pressure process, right? So for ideal gas, if you know, you can again easily use this relation PV by T is equal to constant. So for constant pressure, it will become V by T is constant, and for constant pressure, constant volume, it will become P by T is equal to constant. Okay, for this process, because this is, so these are the ways by which you can handle this kind of questions and find out the values of temperature and pressure. And one more clue or one more hint is the compression ratio and the expansion ratio. So you're already given the compression ratio, that is 16 in this case, so you can take the aid of that as well. Okay, so let us see. Okay, so we'll have T2 by T1 is equal to, from this relation, TV3 power gamma minus 1 is equal to constant. So we'll have T2 by T1 is equal to V1 by V2 to the power gamma minus 1. Okay, now since V1 by V2 is 16, it is a compression ratio, so we'll have T2 by T1 to be equal to 16 to the power 0.4 or 3.03. Okay, or we have T2 to be equal to 3.03 times 288 or 873 Kelvin. Okay, it is the temperature at point 2. So for point 2 to 3, which is a constant pressure process, we'll have P2 V2 divided by T2 to be equal to P3 VT divided by T3. Okay, so for constant pressure, P2 will be equal to P3 or V2 by T2 equal to V3 by T3. Okay, so V3 by V2, that is the cutoff ratio, will be equal to T3 by T2. So T2 is 873. So I made a mistake here. It is 873. So 773 divided by 873. 773 how I got, because they mentioned that after the heat addition process, the temperature becomes 1480, right, or 753 Kelvin. So from that, I get RC to be equal to 753 by 873 or 2.01. Okay, so first part of the question is done, cutoff ratio. Second is the heat supplied. It's again very easy. You need to find the heat supplied. It is the heat addition at constant pressures. You know T3 and T2. Cp you also know, so you'll get Q1 as Cp T3 by T minus T2, which is a constant pressure heat addition. So you'll have 1.005 times 753 minus 873 or 884.4 kilojoule per kg. Okay. Now they also, if I go back here, heat supplied per kg of air. Okay, so you need to find it. So yeah, so this is heat supplied. Okay, then you can find the efficiency. Okay, so here what I have done is I have found the heat rejected as well to find the efficiency. So what I can do is I need to find now T4, right? So as I mentioned here, T3 by T4, that is this process, T3 by T4 would be equal to V4 by V3 to the power gamma minus 1. Okay, similar to this relation, from this relation. Okay, so V4 by V3 can be written as, since V4 equal to V1, so we can write this to be equal to just write it somewhere. This we can write something like V1 by V3 because V4 is equal to V1. Okay, so we can write something like V1 by V2 times V2 by V3. Okay, or V1 by V2 divided by V3 by V2. Okay, so we'll get what V1 by V2 is RV, the compression ratio, and V3 by V2 is RC, the cutoff ratio, right? Both of them you already know. So from that you can write T3 by T4 to be 16, that is volumetric compression ratio, divided by RC, the cutoff ratio, that is 2.01 to the power 1.4 minus 1 or 0.4. You will get T3 by T4 is 2.29, or T4 would be 753 divided by 2.29 or 766 Kelvin. Now heat rejection Q2 would be CV T4 minus T1, correct? T1 you already know because it's a constant volume heat rejection. Okay, so T4 is 766 Kelvin and T1 is 288 Kelvin from the initial condition. So we'll get Q2 to be 0.718, 766 minus 288, that is equal to 343.2 kilojoule per kg. Now since you know Q2 and heat rejected and heat addition, you can easily find the cycle efficiency as 1 minus Q2 by Q1, or 1 minus 343.2 divided by 844.4 equal to 0.612 or 61.2%. Okay, so instead of doing this calculation, you can also take the help of the formula for the cycle efficiency of diesel cycle, if you recall. So you will have eta cycle as 1 minus 1 by gamma dot 1 by RV to the power gamma minus 1 dot 1 by dot RC to the power gamma minus 1 divided by RC minus 1. Okay, so you know RC, that is 2. If I go back here, 2.01, and RV is 16.4 and gamma is 1.4. So if you substitute these values here, you will get eta cycle as just let me go step by step. So RV to the power gamma minus 1 is 16 to the power 0.4, that is 3.03. okay, and RC is 2.01, so this factor becomes equal to 1.64. so you see here this factor is greater than 1, right? Or 1.64, this factor, this and this, if you take into consideration, 1.64 divided by 1.4 is greater than 1, right? Because 1.64 is greater than 1.4, so this factor becomes greater than 1. That's why you get the efficiency as 0.612 or 67.2%. Okay, so let me just point it out, if the compression ratio of the Otto cycle would have been 16, then the compression ratio then the efficiency of the Otto cycle would have been greater than 61.2%. okay, but as I mentioned, in general the compression ratio of the diesel cycles are always greater than the compression ratio of this Otto cycle. That's why the efficiency of this diesel cycle, that's a general case, a very random case that is given in the question, is greater than the efficiency of the Otto cycle. Okay, see, it is 61.2 here. In the case of Otto cycle it was 56.5%, if I'm not wrong. Okay, so the final part was the mean effective pressure. Okay, so mean effective pressure. Okay, so in this case the mean effective pressure, is the ratio of the net work output of the cycle divided by the stroke of the piston. Okay, so this gives the mean effective pressure. Okay, so we have it won't come in the exam, but I just one more concept to know, that is the mean effective pressure of a engine is given by the net work produced divided by the stroke of the engine. Okay, the stroke of the engine would be the largest volume divided by smallest volume. Largest volume is the volume at the outer dead center or the bottom dead center, and the lowest volume is the volume at the inner dead center or the top dead center. Okay, so it is the expression. Okay, so W net by V1 minus V2, this is the stroke of the engine. So W net can be found out by using the cycle efficiency and the heat input. Cycle efficiency is 0.612 times 884.4, or W net is 541.3. So since V1 can be found out as RT1 by P1 from the ideal gas law, we have V1 as 0.27 times 288 divided by 100, or 0.827 meter cube per kg. And we know that V1 by V2 is 16, so we can find V2 as 0.827 by 16 or 0.052 meter cube per kg. Now since we know V1 and V2 and W net, from this you can find the mean effective pressure as 541.3 divided by 0.27 minus 0.052 or 698.45 kilopascal. Okay, so yeah, so I think that's all for today. If there's any doubt, you can ask in this question. If there's any doubt, you may ask. Otherwise, that would be all. Okay, so this was an extra session as per the request of one of the students. So I conducted it regarding Otto cycle and diesel cycle, but this won't come in the exam. Okay, for exam it's only up to the vapor compression, refrigeration cycle, the Brayton cycle, and the Rankine cycle, like the last lecture by Professor Anand, and these were the additional topics that were requested by the students. Okay, so I hope it's all right. Then, if there's any doubt, you may ask, or that's all. Okay, so this is the final session for today's this course. Okay. Okay, then if there is no doubt or anything, then I think we can end the session, and thank you for attending these problem solving sessions. Yes.
Okay, sir. Thank you.
Yeah, thank you so much. Thank you so much.
Thank you. Is there any other formula for mean effective pressure other than this?
Hmm, I only know this one right now, but it might be
Okay,
there.
sir.
But I know only this one. This is the concept that.
Okay, okay.
Yeah, that's why I thought. What will the
Okay,
mean
sir.
effective?
Thank you for the extra session and your efforts.
No. Thank you so much for all of you for attending these sessions so sincerely. Okay, and participating
Okay,
as well. Yeah. Thank you. Okay,
thank
then
you.
all the best for the exams.
Thank you very much.